Welcome back, folks. On this video, we're going to cover part 2 of lesson 1.2, finding limits analytically. Okay, remember that means finding limits by hand. So part 2, here we go. All right, so picking up with problem 4, evaluating limits using Pythagorean identities. So now we left off with some limits involving trigonometry. Looks like we have the same thing here. And for this one, we're going to have an example of mixing Pythagorean identities into it. Okay, so we want the limit of this function as x goes over to pi over 2. Let's just remind you quick of what the cosine of sine of pi over 2 would look like. I'm going to sketch the curves quick. And sine was the one that started in the middle, goes up and down. There's my sine x. Takes 2 pi units to complete one cycle. And pi over 2 was where this first hump happened. And it runs between 1 and -1. Cosine x was the one that started at the top, goes down and back up. And we can tell that's a 0 at pi over 2. So when I substitute pi over 2 in, when I try to use direct substitution, I'd get a 0 on top. And on the bottom, sine of pi over 2 is 1. So I'd have 2 minus 2 times 1, which would be a 0 as well. So with direct substitution, this limit gives us the 0 over 0 indeterminate form, meaning that I can't evaluate this limit directly. I'm going to have to do some rearranging. All right, this is where our Pythagorean identities are going to come into play. Anytime first off, what we're talking about, the simple one was that sine squared x plus cosine squared x was equal to 1. And anytime I have sines or cosine squareds with some addition or subtraction in between terms, that's going to be what tips me off to, I might use this Pythagorean identity. What I'm going to do with this one is I'm going to replace the cosine squared up top with what I end up with cosine being equal to in this equation. Let's get cosine by itself. I'm going to subtract sine squared x from both sides. I'll cancel my sine squared out on the left. Leave me with just a cosine squared x, which is what we're looking for, equals 1 minus sine squared x. Guess what I can do up top then is replace that cosine squared. We'll write it as 3 parentheses 1 minus sine squared. And then on the bottom, we've got 2 in both terms. Might as well factor that out as well. So 2 parentheses times 1 minus sine x. And I guess what I've accomplished here and how I know I'm on the right track is notice I got rid of the cosines. Now I just have some sines that looks like we could cancel. Now this one I can't do that yet because I have a 1 minus sine squared on top and just a 1 minus regular sine on bottom. What I can do with this numerator is we'll keep the 3. I can rewrite this 1 minus sine squared using my difference of squares formula. This is a 1 squared minus sine squared, so I can rewrite it as 1 plus sine of x times 1 minus sine x, okay, over that same 2 times 1 minus sine x. And now since I have factors of 1 minus sine x in the numerator and the denominator, I can cancel those out. And with what I'm left with, I have no more 0 issues in the numerator. I just have denominator, I just have a 2. And we'll also be able to evaluate the numerator. So we can rewrite this limit as the limit as x goes towards pi over 2 of a 3 times 1 plus sine x over just the 2. Okay, now we can use direct substitution. This will be 3 times parentheses 1 plus the sine of pi over 2 divided by 2. So 3 times 1 plus sine of pi over 2 is just a 1 all over 2, which will give us a 2 times 3 is 6 over 2, which reduces down to a 3 finally at the end. All right, so that limits equal to a 3 there. All right, so there's an example of utilizing Pythagorean identities within a limit problem involving trig. Why don't you take a minute, pause the video, work through part B in your note guide, and then hit play when you're ready to check and see if you got the right answer. In problem 5, we're going to look at evaluating limits of piecewise defined functions. So for this one, we have f of x is defined below. So we have this function, piecewise function, for our f of x. And we want to find each limit analytically by hand once again. Okay, for part A, we're going to take a look at the easy example. I'll say easy because the limit on f of x as x goes towards 1. Notice 1 falls right in this range between -2 and 2. It's not one of our boundary cases where we switch from one rule to the other. Okay, so for this one, we're just going to apply direct substitution. We'll plug that 1 into the x squared minus 3. So that'll be 1 squared minus 3, which is equal to just a -2. Nothing to it. All right, B, C, and D, we're going to do some work with x at -2. And for this one, we're going to look at it coming from the left side, the left-handed limit, also the right side, before we get to just the limit as x goes towards -2. And the reason I have to do that is -2 is where our function switches over from one rule to the other. So what we're going to have to do is evaluate these limits separately and then use those answers to figure out the limit as x goes towards -2. Let's go ahead and do that. Let's look at the limit of f of x as x goes towards -2 coming from the left side. In other words, when it's below -2, that's going to be using this rule here. Okay, so we'll substitute -2 directly into x plus 4. So I'll just be a -2 plus 4. -2 plus 4 is equal to a 2. All right, for C, the limit as x goes towards -2 from the right, for that we're going to utilize our rule for everything above -2, the x squared minus 3. Now this only applies when we're strictly greater than -2, but with limits I can still substitute that value in to figure out what it's doing as it comes towards it. So let's plug in that -2 to the x squared minus 3. All right, that's going to be a 4 minus 3 is a 1. All right, so we see here is that our left-hand limit and right-hand limit give us different answers. Okay, that means the limit as x goes towards -2 of f of x does not exist. If we think about what's happening here visually, what we'd have is something like this at -2. I'm just going to draw a rough sketch. What do we have? A 1 and a 2. Visually what we'd have is kind of not to scale something that looks like this. Okay, whereas we come from -2 from the left and right, we get different answers. Okay, limit does not exist. We just confirm that numerically here with this one. All right, that's part A, B, C, and D. Why don't you take a minute, pause the video, work through the next 3 problems, which you're going to take a look at what's happening here with 2. Pause the video, work through those, and hit play to check your answers out. All right, last thing we're going to talk about in this part of the lesson is something called the squeeze theorem. Here's what that is. If f, g, and h are functions, okay, so I have three functions defined on some open interval containing a, such that g of x is always less than or equal to f of x, which is always less than or equal to h of x for all x's. Okay, so here I have my three functions, g, f, and h, and g is always below f, h is always above it. And the limit as g of x tends to a is equal to the limit as h of x tends to a, which is equal to L, then we know that the limit of f of x as x goes towards a is equal to L as well. Okay, so in other words, kind of visually, like we said, g of x is always less than or equal to f of x. H of x is always greater than or equal to f of x. And if those two functions come together and touch at x equals a, okay, well that means that f of x has to squeeze through there and is going to have the same value for that limit. Okay, what is the point of this? Why is it helpful? Well, this is a theorem we could utilize to evaluate some limits that we can't evaluate directly. Okay, that there is no way to rearrange and use substitution. And we'll show you in the next couple examples of ways it could show up on the AP exam, kind of questions you'd have to answer, okay, utilizing the squeeze theorem. So problem 6, using the squeeze function, let g and h be functions defined by g of x equals sine of pi over 2x plus 1, and h of x equals x squared minus 2x plus 3. If f is a function that satisfies g of x is always less than or equal to f of x, which is always less than or equal to h of x for all x, we want to know what is the limit of f of x as x goes towards 1. Okay, now for this one, they didn't even give us the f of x. Let's just assume that it's some function that can't handle 1. We can't evaluate that limit directly. No matter how many ways we rearrange it or manipulate it or cancel things out, it just can't handle 1. But let's say we know that it's always between a g and an h. What we'll do is we'll evaluate g and h's limits at 1 and see if that tells us anything about the f. All right, so individually, let's look at the limit on g of x as x goes towards 1. Okay, now here there's not going to be any issues plugging 1 in, no domain issues or anything like that, so we can use direct substitution. So I'll just be equal to the sine of pi over 2 times 1 plus 1. Just a reminder once again, sine function goes between 1 and negative 1, and it hits that value at pi over 2. Okay, so in other words, here we have a 1 plus 1 equals 2. Let's do the same thing for our h of x. We'll look at the limit on h of x as x goes towards 1. Now, h of x is just a polynomial. Okay, no issues substituting a 1 in there directly either. So it'll be a 1 squared minus 2 times 1 plus 3. All right, so 1 minus 2 would be negative 1, plus 3 would be 2 as well. All right, so we know that f of x is always greater than or equal to g of x and less than or equal to h of x. And the limit on both g and h as they go towards 1 is 2. It's the same thing. That means that f of x has to have the same limit. So we can do is we can say that by the squeeze theorem, and we'll include that by the squeeze theorem just to let the reader know which theorem we're using. We know that the limit as x goes towards 1 of f of x, okay, whatever function that is equal to 2 as well, because f has to squeeze between the two of these. It has to squeeze into that 2. All right, for part B, let's take a look at an example where the squeeze theorem doesn't work. It actually doesn't tell us anything about the function. All right, so again, we have a g and an h. And again, we have some function f of x that we're not sure how it's defined. We do know that it's always greater than or equal to g of x and less than or equal to h of x. And for some reason, I can't do the limit as x goes towards 1 directly. So we'll see if we can use the squeeze theorem here. Again, let's find the limits for g and h separately. So we'll look at the limit on g of x as x goes towards 1. Okay, that's just a polynomial. We can use direct substitution. So negative 2 times 1 squared plus 4 times 1 plus 1. All right, so that's going to be a negative 2 plus 4 would be a positive 2 plus 1 would be 3. We'll also look at the limit on h of x as x goes towards 1. Polynomial, so we can do direct substitution. So 1 squared minus 2 times 1 plus a 6. So we've got 1 minus 2 would be negative 1 plus 6 would be a 5. All right, now in this case, since I didn't get the same limit for both these functions, we know that f, since it's always above g but below h, will squeeze between them. So it'll be greater than 3 and less than 5, but we can't actually figure out what that limit for f of x is. So we'll just say it cannot be determined. All right, so cannot be determined from the given information. Squeeze theorem, powerful tool for evaluating some limits that you can't necessarily evaluate directly. But like we see here, it's not going to work in every single case. Okay, here's a case where it cannot be determined. All right, so that's it for part 2 of lesson 1.2, evaluating limits analytically, finding limits by hands, in other words. Okay, so go ahead and take a look at the rest of the homework, try to get that finished up. And like always, if you're getting stuck, if there's some stuff you can't figure out, make sure you are asking for help. We'll be here to help you out. All right, we'll see you next time.